Hey everyone, this is Dr. Walker. This is video 513 and we're going to go over the concept of electric flux. I like to start off with a fan analogy. Imagine a fan and it's blowing a bunch of air through a loop. If you want the maximum flow through that loop, then you want the airflow to be perpendicular to that loop. That way all of it is going through that loop. Now, if you don't want any airflow through that loop, then you want the airflow to be parallel to the loop. Then none of it is going through that loop. So that's how I want you to visualize electric flux. Instead of air, it's going to be electric field, and it can still be a loop or it can just be any kind of surface through which the electric field is going through. So let's consider, first of all, a flat surface and the electric field is going perpendicular to that surface. So that's how we know that we have the most flux, because we have the field perpendicular to the surface. So we define the electric flux as the product of the electric field and the area. So we see that electric flux is proportional to the number of electric field lines penetrating the surface. The more field going through that area, and the bigger the area, the more flux there is through that surface. But what about if the field is not perpendicular to the surface? Well, we only care about the component of the field that is perpendicular to the surface, right? So if we look at this picture on the top here, we have electric field going horizontally to the right and the surface is slanted. So we only care about E perpendicular. That is what is going through that surface. If we just consider E, then we know that it also has a component that's parallel to the surface, but we already said that E parallel, there's no flux there because it's not going through the surface. All right, so we only care about E perpendicular, and in this case, that's equal to E cosine theta. Another way to think about it, instead of thinking about the component of the field that is perpendicular to the surface, we can think of the component of the area that is perpendicular to the field. We get the same result. If you look at this bottom picture, there's a vertical area drawn called A perpendicular, and that's perpendicular to the field. And A perpendicular is equal to A cosine theta. So now if we think about the flux through a flat surface, then for the top case, it's going to be E perpendicular times A. For the bottom case, it's going to be E times A perpendicular. In both cases, that's equal to EA cosine theta. So in both cases, we can now define the electric flux through a flat surface where the field is going at any angle. As long as it's a uniform electric field, it's going to be the dot product of E and A. So let's take a look at that in just a tiny bit more detail now that we have the electric flux is E dot A. What is this A vector? Well, it's called the area vector. As we can see in this bottom picture, the green arrow here, the area vector has a magnitude A, which is the size of the area, but the direction is n. So you can draw a unit normal vector, n hat here. So it's a vector perpendicular to the surface. That is what the area vector is. It's perpendicular to the surface, but its magnitude is the whole surface area of that surface. And the units for electric flux is going to be newtons times meters squared divided by coulombs. That comes from electric field, newtons per coulomb, times area, which is meters squared. Let's look at a couple of examples. As always, please pause the video so that you can think about it before I go over the answer. This problem says, what is the electric flux through the shaded surface? So the shaded surface is right here, and we're looking for the flux through it. So we see in this case that the field is completely perpendicular to that surface. So just like that fan, just like that air, all of that field is going through that surface. We have maximum flux, and in that case, we just multiply the E, the electric field, times the area. So in this case, the electric field is 100 newtons per coulomb, and the area is 4, 2 times 2. So we get 400 Newton meters squared per Coulomb as the flux through the shaded surface. Let's take a look at one more problem. This one says, which surface, A or B, has the larger electric flux? So pause the video and think about it. So you may be thinking, well, A is perpendicular, and Dr. Walker said you want the field and the area to be perpendicular, so A must have the bigger flux. However, you do notice that B also has a bigger area, even though B is slanted. So if you think about the flux through A, it's just going to be this E here times the A, right? Because they're perpendicular. When they're perpendicular, you just multiply E times A. So that's the flux through surface A, is E times A. Well, what's the flux through surface B? The flux through surface B is E times B perpendicular. We said we can think of the flux as the field times the component of the area that is perpendicular to the field. Well, what is the component of this area here that is perpendicular to the field? It's actually A, right? That's the perpendicular component of B. So it turns out in this example that the fluxes are equal. Now I do want to add one quick follow-up to this example. Let's say that we wanted to calculate the electric flux through surface B. Let's say that we were given a couple of values. So this is just a follow-up, it's not written in here, but that's okay. So let's say we're given this angle here is 20 degrees, and this shaded surface B here is 2 meters by 2 meters. How do we find the electric flux? Well, the electric flux is going to be E dot B, otherwise known as EB cosine theta. So the trick is just to make sure to use the correct theta. We can draw the vector B here as being perpendicular to the surface. It's perpendicular to the surface. But the angle that we want, let me put that over here. The angle that we want is not 90, right? The electric field is horizontal. Electric field is going this way. So let me use my red ink here. You know what, let me use my pink, just because the electric field is pink here. So electric field is going this way. So we want this angle, theta, and you should be able to see that that angle, theta, is actually 70 degrees. So, and I can show that on the side in case you don't see that, because it's good to practice a little bit. If I draw two lines here, one line for the base here, and one line for E, so they're parallel. And then I draw the line for the surface here. And we know that this is 20. So that means this is 20 as well. So over here. And now consider a line B perpendicular to this slanted surface. The line B is going this way. Let me draw it in blue, just for fun. Well, if this is B here, that's perpendicular to the surface, then this is 90 here. And if we have a straight line, then we can see that this must be 70 right here. So that's the long way of seeing that this is 70. So now that we know that this is 70, that means that the flux through the shaded surface B here, let's call it E comma B, is going to be the electric field, which is 100 times B, which is 2 times 2, which is 4, times cosine of 70. And all of that would be in newtons meters squared per coulomb. So just an extra little quick example just to practice calculating flux. And we'll do another example in the guided examples that follow.